So as we're dialing down to 7:30-ish, for the time being, can you guys take a look at this question? And I know that this might not be intuitive. Maybe this is a part of chemical kinetics, and that's going to be kind of the focus of our topic today. And now I know some of you guys might not be the most familiar with this, but let's take a look at this question and see what you can recognize. Maybe focus on some of the compounds, identifying what those symbols mean. CuOH2, what does that mean specifically? Think about that for a bit. Then in a few minutes, we'll talk about this. So for today, my idea is that we can go through several US National Chemistry Olympiad questions, using those as a basis for our discussions for talking about kinetics, and perhaps we might get to a little bit of acids and bases. We'll see where we go. Anyway, take a look at this question. All right, so let's just jump right into this question. First of all, anyone familiar with kinetics? Anything at all with kinetics? Any ideas? All right, so then let's go to start with the fundamentals. First of all, CuOH2, that kind of stuff. Of course, these are chemicals. Cu, what is that again?
Copper.
Copper, yep. O, that's oxygen. H, that's hydrogen. So what we have right here is actually OH minus. OH minus is what's called the hydroxide ion. It's a very common ion. Basically just a negatively charged compound, negatively charged set of particles. Okay. So we have CuOH2, Cu being a metal, and then we also have this negatively charged compound. This is, as we see right here, it's we can see that's solid as well. We're given that, the little S right there. So we have a solid with copper and hydroxide. This is actually going to be an ionic solid, basically positively charged copper ions and negatively charged hydroxide ions. This is our compound. Over here we have NH3. Any idea what this is? Ammonia, yes. So NH3, that's going to be ammonia. And this typically is going to be a gas, but we see here that it's AQ or aqueous in water. So that's dissolved in water right now. So we're taking this ionic solid and putting it in a bit of water with some ammonia. And then this reaction occurs where the copper gets a lot of ammonia attached to it in some sense. and then the hydroxide floats free. Basically, the copper and the hydroxide separate, and the copper experiences what's called a complex formation. Basically, we can think about the copper being like that, and then ammonia just being like kind of surrounding the copper in a sense. And what's actually going to happen is that the ends, ammonia has a different shape than this, but for demonstration purposes, it's going to form an attraction. And now just imagine that 4 times around the copper atom. That's essentially what's going on. So when we see CuNH34, it's a copper complex where basically you have that copper ion in the middle and then these NH3s around it, attracted to it. All right, so that's what's going on. Basically, the copper exchanges its hydroxide for ammonia. That's kind of the bottom line here. Anyway, now let's get to the kinetics part. So we have this chemical equation, but it's a little bit different because there's this, right? Usually, if I write a pretty simple kind of chemical equation, such as this one right here, we actually looked at this last week. I have a direct arrow, but over here I have 2 arrows. What do you guys think that's about?
Goes both ways.
Goes both ways? All right. And what does that mean though?
The reaction is happening both directions simultaneously.
Yeah, the reaction is happening both directions simultaneously, but also the reaction is not necessarily like it's happening at different rates. So here is where we get into kinetics. Kinetics meaning just the study of chemical rates, essentially. So basically, let me just call this A and B, and I'll call this C and D. And this is just to simplify the scenario. So we have A plus 4B equals, goes to, not equals, equals is math. We're not in math. A plus 4B, that's not really a plus, but you know what I mean? A plus 4B is, can react to form C plus 4D, or 2D, sorry. The same thing can occur the other way. So essentially the copper can uncomplex, so basically it can separate from the ammonia and then realign itself with the hydroxide ions. That's possible, right? We can have the opposite reaction, or what's called the reverse reaction. Reverse, that might occur. The thing is, these reactions occur at different rates. It just so happens that this rate, this first equation, like the actual complexing, is going to be faster or more favorable. So we're going to see a lot of A plus 4B forming C plus 2D, but not so much in the other way around. So that's why, in general, this reaction might shift this way overall. Perhaps under different conditions, the reaction might shift that way instead. So this is the whole study of kinetics. What affects how fast one rate goes relative to the other? Now you might ask, why is why in this case, why would the complex be more favorable? Well, the thing with complexes, especially metal ion complexes, is that the attractions that they form are very energetically favorable. So maybe if you study a bit of physics, you know that generally lower energy state is considered more favorable. So like, for example, if you're on a table and you roll the object off the table, it's going to fall off the table. Essentially, you go from the higher energy state, the higher elevation, and you fall to the lower energy state, the ground, right? Similar thing goes on in chemistry, of course, much more nuances and all that, but glossing over that, lower energy states are better or more favorable in general, not always, but that's how it is. So the complex is simply is very energetically favorable compared to the original compound. Anyway, on to whatever this stuff is going on. So this is actually this is not really kinetics, this is equilibrium, but it goes at a point. So let's go back to the A plus 4B thing. and the C plus 2D. Let's say I start out with just arbitrary values here. 1 mole of this, and then 4 moles of this. A lot of this is going to react. So how much C and how much D would we predict to have here? We have 1 mole of A and 4 moles of B. All right, I just see a chat message. 1 mole. 1 mole of which compound?
C.
One mole C, okay. What about D?
2 moles?
2 moles, yeah. No, you got it. 2 moles. So that's what we expect. But then there's a condition with that. That's saying that this reaction goes to completion. Essentially, A and 4B, all of it reacts to C and 2D. That was an assumption we took last time. That was an assumption that we did for stoichiometry and all that. That's an assumption we're going to disprove now, though. So with any reaction, everything doesn't just go one way, right? There's going to, because we know that there's going to be the reverse reaction going on, right? C plus 2D, even if it's not as favorable, it's going to be going on to some minor extent. So never will you have a 100% go to completion thing. It's going to be an assumption you see once in a while, but in real life, that just doesn't happen. So it might be like 99% if it's very favorable. It might be 90% or something like that. Sometimes it's 50-50. It's really depending on many different circumstances, much of which is actually the current study of what chemists are studying right now. A lot of it is about what conditions can maximize so-and-so reaction, things like that. All right, so hold on, I'm just plugging my earbuds right here. All right, so now we know that completion, that's an assumption. Okay, so this is not going to be 1 mole, that's not going to be 2 moles. Because if these are 1 mole and 2 mole, that implies that these are now 0, and they're never going to be 0, right? It's unrealistic. So what we're going to end up having is these reactions are both going to be happening simultaneously until, let's say that this reaction starts out more favorable, right? And it would start out more favorable because we have 0, let's go back a little bit. Let's start with the 1 mole, 4 mole. And I said how much these were, but I never said how much these were. So I'm going to say that C and 2D currently are 0. So we start with 1 mole of A, 4 moles of B. They react, and they're going to start producing C and 2D. The thing is, if we're looking at the reverse reaction, we have no reactants. We have no C or 2D that could possibly react into A and 4B. So the only reaction that's going to start out occurring is that way. And then we're going to accumulate some C and 2D. So then the reverse reaction is going to start happening. But the thing is, the forward reaction is going to be more favorable. So in general, it's going to go more, the reaction is going to shift more towards the C and 2D over time. But as you start running out of A and 4B, that side reaction, the forward reaction, starts to slow down. So we're going to, I'm going to do that. We're going to see this slow down a bit until it's very little. And then now that you have more and more C and 2D, you're going to have more of this reaction occurring. And eventually, you might overshoot to the point where C and 2D, that's going to be the more favorable side. And then in that case, now you're starting to produce more A and 4B, and then you might shift it over again so that A and 4B is once again the more favorable side. And then you might shift it over again and again. And that's what's called a dynamic equilibrium. So that's where that comes from, the equilibrium expression. So that's called the dynamic equilibrium. You can compare that to a static equilibrium. Static meaning that you hit equilibrium and then you're staying still. With chemistry reactions, you're never staying still. there's always A4B making C2D, and then there's always C2D making A4B, and they're happening at the same time. When you're at dynamic equilibrium, those two reactions, the forward and reverse, will be approximately equal. So that's what every chemical reaction is going to drive to. It's going to drive to equilibrium. All right. So I started out saying that I was going to talk about kinetics, but I ended up talking about equilibrium. That's okay. We'll get to kinetics. So that's what equilibrium is basically about. You have both sides of a reaction occurring, and one side might be more favorable, but over time, it's going to drive one way or another until both sides are happening at the same rate. All right. So now let's look at what this equilibrium expression is. Now that I'm thinking about it, equilibrium was a better place to start. It's a little easier to understand at first for how do you manipulate this stuff. All right. So essentially, the chemists have done these reactions many times to try to find these equilibrium patterns. A lot of what I'm going to say now is not particularly intuitive or logical, but it's what the data says. It's what the data shows from reactions that scientists have done in the past and scientists are doing now. So yeah, that's where anything I'm going to say now comes from. Anyway, for equilibrium expressions, KEQ, K just means equilibrium constant. Each reaction is going to have its own equilibrium constant. This reaction would have a certain equilibrium constant, but then a different reaction would have a different constant. And it depends on the reaction. So KEQ is going to be equal to a fraction. And on this top, we're going to see that we're going to have products. On the bottom, we're going to see that we have reactants. What do I mean by that? Well, I'm just going to write out the equilibrium expression for this particular question, then we'll explain it. So this one's going to have CuNH3 for 2 plus OH minus squared NH3 to the fourth. That's actually going to be the KEQ expression for this. I'm sorry for spoiling the problem. Yes, the answer is C. But what does this mean? Well, it just means that, let's say the amount of this compound I have doubles, right? Let's say it multiplies by 2. Then this reaction is going to then shift such that this amount might go down, this amount might go up, and then overall though, KEQ is going to stay the same. Okay, let me break that down a bit because that was definitely not the most cohesive way of explaining that. So when let's say I double that amount, the amount of this compound again, what's going to happen to KEQ? What would you expect to happen to KEQ? If you double this side of the equation,
It doubles.
doubles, yeah. So let me go back to the ABCD notation. ABCD, concentration of C, concentration of D squared, and then that is A to the fourth. You double C, so then you would expect KEQ to double. The thing is, KEQ, that's a constant. Each reaction has its own constant there. So that constant's not going to change. So how do we account for this doubling? Well, this is where the equilibrium, this is what's considered an equilibrium shift. Basically, if you have this doubling, then what's going to happen is this reaction is going to then be more favorable on this side. Essentially, you have more of the product, right? You have more products overall. So this reaction is going to shift that way. So we're going to see that some of the C and the D is going to start reacting to form A and B. So then C will lose a bit, D will lose a bit, and A will gain a bit until KEQ remains the same. So KEQ never changes. It's constant for every reaction. There's a specific value for every reaction. So Yeah, that's the bottom line. And of course, there's going to be a lot of math that goes into it. You guys could probably see that coming. So let's say I have KQ. I'm going to just write this out again for clarity's sake. Let's say we start out with these. Let's say I'm going to just take off the brackets. So let's say I start out with C amount of CuNH3 D amount of OH minus, and then A amount of NH3. So, oh shoot. No, this is not A, this is B. Sorry about that. All right, anyway. So if this is our case, and let's say C doubles, 2C now, what we're gonna see is that some of that C is gonna go away. I'm gonna represent that as just minus X. Basically, after you double the C, you're gonna lose a bit, minus X. And then you're also gonna lose a bit over here. But the thing is, if you're losing one of these, how much of this are you gonna lose? Right, if one of these reacts with two of these, what would we expect?
You would lose two of the other.
Two of the other, yeah, that's really good, Amos. This would be minus 2x. And does that make sense? Because every one of these got to react with two of those. So if you're losing x here, you're going to lose 2x here. Make sense to that rule?
Yeah.
Cool. So now let's do the same thing with B. If you're losing one of this and you're losing two of these, how much would this one change? Now I'm actually going to change the color. How much would this one change?
By 4.
By 4, okay. And now tell me, will it increase or decrease in amount? Increase or
It would decrease.
decrease? Okay. Why do you think so?
Because you're losing products, right?
You're
Or
losing products.
Yeah, or losing the CuNH3 and
Yeah.
hydroxide. So why would that increase if you're losing that from the other side?
Well, let's think about it. So right now what we're talking about is basically a reaction going this way. So some of these react to form some of these, right? Here, this would, in this case, right now that this side is the product side and this side is the reactant side. But when we're considering the reverse reaction, these guys are actually like the actual products, the actual reactants, sorry. These are the reactants and these are the products. And then keep in mind, the chemical reactions, they're going both ways. So both of the sides are products and reactants, depending on whether you're looking at forward or reverse reaction. Since we're looking at reverse reaction, this side is going to be losing amounts in order to form this side. So,
Okay,
yeah,
that makes sense.
So it would be an increase, right? We're going to see an increase in 4. What we're going to see is this is B plus 4x, because that 4 that you mentioned before, that still applies. It's going to be increasing by 4x. All right, and then KEQ stays the same. So then what we can do is, I got it. Yeah, no, I'll clear the board after this. Basically, KEQ, we know it's equal to that. So what we can do is say that that's equal to 2c times d squared over b to the 4th. And now we have a very large equation that we would be able to solve for x. Now, in this case, this one's kind of complicated because you have x cubed in the numerator and x fourth in the denominator. So this one is not the most solvable, but in many other cases with different chemical reactions, there's going to be some common chemical reactions that different like USNCO likes to bring up because they're more simple, and then you can explore this principle into greater depth. Anyway, that basically covers the premise, at least for this question, what is the correct equilibrium expression? It's this one right there. All right, so now let's talk about this actual expression. How do we know it's this particular expression? There's pretty much a trick that you can know. Essentially, just look at the coefficient here, and that will determine its power in the actual KEQ expression. So this one, we see that there's no constant. So that implies that there's just one. Hold on. That implies that there's just one Cu NH3 4 plus 2 plus. And then there's 2 over here. So that's where the squared comes from. And then over here we see the 4, right? The 4, that's what contributes to the power to the 4. That simply works because experimental data tells us that that's how it works. And you can think about it too, that if you need a lot more of this, then during a reaction, that's the amount that you have of that is going to make a much larger impact on what happens to the reaction, right? If you're missing a little bit of NH3, that's going to be a lot more important than if you're missing a little bit of this, because you need more of it, and more of it reacts at a time. Like I said, if it's not intuitive, that's because it's not something that humans thought of. It's something that the data tells us this is how it works. All right, then you guys probably also notice this one's not here. That's because you only usually include aqueous or gaseous compounds in your KEQ expression, in your equilibrium expression. So solids, what other compounds? Liquids, they don't really count if you have those in your expression. And that's because these are compounds that are more omnipresent. Like, let's say you have this reaction going on, you have this solid. The solid, basically, the surface area and the reaction rate that bases off that, that's going to be affected by surface area. But the actual equilibrium, the solid doesn't affect. It's not really, like, if you have more solid, your equilibrium is not going to change. That might not make perfect sense, but once again, that's what experiments tell us. And there's a way to think about it. Yeah, it might be something that you guys might want to think about a little bit more, ponder over it a bit. How it's like if you have a solid and you have more of that solid, how would that change the equilibrium? That wouldn't. So that might be something that you might want to think about. Anyway, that's the basics of writing KEQ expressions. Look at the coefficients, like this one right here, this one right here, and ignore solids and liquids. Other than that, though, it's pretty much plug and chug to figure out your KEQ expression. All right, any questions on this problem that you guys might have? Any questions at all? All right, cool. So let me stop my share real quick. Never mind, I got this. Let's look for the next question. I just have a few questions in here to look through. Oh, this one. Okay, this one's also about equilibrium, so we'll take a quick look at this. A little bit of a different approach. All right, take a read through. All right, so a lot of words here that that you guys might not know per se from past experience. Do any of you guys have any thoughts for approaches, or maybe what do you recognize from what we've talked about already? There should be some things that you guys.
I mean, we have
No.
it can't be D, right?
D. Well, let's not rule it out just yet. I honestly don't know. It's been a while since I've done this question, but I'll reason out with you guys right now.
Why would there be nitrogen if it's not mentioned anywhere?
The thing with nitrogen is that it could potentially add pressure into the system, in which case the pressure might, like the environmental difference in the pressure, that might cause a shift in the reaction equilibrium. There's always that chance.
Oh, okay.
Is change in H like degrees just like temperature?
It's kind of like temperature. It's what's called enthalpy. It's essentially just a representation of energy levels. Enthalpy is very relative. So basically, how does this energy level compare with that other one? That's why you see a change. It's like, what is the difference between these two? Anyway, this thing right here, that we recognize, right? Equilibrium going on. We know that. And this is some pretty good practice for writing an equilibrium expression. So what do you guys think this equilibrium expression will be? Remember that those two things we talked about? Look at the coefficient and take away solids and liquids. What do you guys think?
It's just
Oh, sorry.
H2O, right?
Say it again.
It's just H2O.
H2O, yeah. It's just going to be concentration of H2O. Actually, since this is gas, we're going to see that instead of concentration, the KEQ will default to pressure of H2O, the partial pressure of H2O. Basically, if you have all the stuff in the container, what's the pressure of the H2O in the container? If you guys study gas laws, this is not the topic for today, so I'm just going to give a very quick introduction to it. There's this thing called the universal gas law that if you change over the equation, you can see that concentration and pressure are proportional. So that's why we're able to do this exchange. That's why we're able to consider pressure instead of concentration. Anyway, oh, I forgot to mention, these brackets just mean concentration. That's what that means. Anyway, so our KEQ, we're going to see that it's going to be essentially just a measure of the concentration of water, but this time we're observing it through the pressure, the partial pressure of water. All right, so the endothermic reaction shown below is at equilibrium with significant amounts of both solids present. The idea of having significant amounts just means that as this reaction is going along, you're not going to run out of one of the compounds. That's all that means. Which action will increase the amount of this at equilibrium? So we want to increase that. What does that mean? Which direction do we want to shift our equilibrium?
Reverse.
Reverse. Yeah, we want to shift it to the left. You can use the directional things to the left.
Okay.
You can shift to the left. Or yeah, you want to increase the reverse reaction, decrease the forward reaction relative to each other, right?
So it's not C. Because you would be increasing the forward reaction if you add more or calcium oxide.
Well, if I add more of this, right, wouldn't I be increasing this side?
Yeah.
In which case, it should push towards the reverse reaction.
Wait, now I'm confused because on the last one, you said decreasing it would also increase the. No, that was the coefficient thing. Never mind.
So what I would, I think a good visual that goes along with equilibrium that you can think about is like a hill. So let's say this is at equilibrium. So therefore you have a very stable hill. If I increase one side, if I increase the amount on one side, let's say I increase this amount, this hill is going to be like that. Anything will tend to move towards that side. If I increase the compounds on that side, they'll tend to move toward that side. Let's say I have this even hill and I take away some of the compounds on the right side. It'll tend toward that side, right? You can kind of think about like that. It's not perfect. And when it comes to solids, it's honestly a little finicky, but for most reactions, most common aqueous reactions, you can use that visual. Anyway, so if we increase this, it would seem to tend toward that side. But if we remember back to our KEQ equation, solids, when you increase their amount, they don't actually impact the equilibrium. They don't change how the KEQ behaves. Therefore, C is actually not going to be a correct answer. All right. Let me first explain what endothermic is. Okay, so endothermic, that essentially just connects directly to this. Endothermic means delta H degree is greater than 0. What that just means is that when you have a positive enthalpy, so when you have this greater than 0, or otherwise known as endothermic, you're going to be inputting energy into this reaction. Why is that significant? We'll see in a little bit, because it will lead us to the correct answer. Anyway, we're good. Basically, that just means that for this reaction, we have to put in energy in order for the forward reaction to occur. And by contrast, what does that mean about the reverse reaction? So if I have CaO plus H2O, if the forward requires energy, if you need to put in energy for the forward, what about the reverse? What do you guys think? You can think about this just, oh, hold on. I see all the chat messages now. Releases energy. Yeah, okay. That's exactly it. We're going to see that the reverse reaction is going to release energy. That's just a way to think about it. One reaction is going to require energy. The other way will release energy. Now, that doesn't always determine that one side is going to be particularly dominant over the other. It's not like the releasing energy reaction is always dominant. Sometimes it is, sometimes it's not. It depends on the case. But anyway, let's keep on taking a look at our answers. Adding N2 to the flask, like I mentioned before, it might increase pressure. There's always that chance. But a common trend is going to be that when you add random chemicals like N2 into reactions, the particles don't really interact too much. They just kind of stay away. And the pressure effect really only applies if they're separated by a barrier, if the pressure is being applied externally. So if you just add it to a flask, it's not going to do much. It's just going to bounce around. It's not like water as a gas is affected at all. So that's also going to be an incorrect answer. Now, Amos, you ruled that answer out immediately, and that was correct. But I didn't want it to be like, oh, it's automatically out. And now I wanted a bit of explanation to it, why we would be able to rule that out immediately. It's not just that it's not in the reaction. It's that it doesn't actually change the circumstances around the reaction.
Okay.
All right, cool. So another way to think about it is that if you have H2O and N2 in a flask, you start out with H2O, no N2, then you add N2. The total pressure increases, but the pressure of the H2O does not increase at all. It doesn't change at all. You're only adding this, so you're only increasing the pressure using the N2. H2O's pressure never changes, so no change to the reaction. Anyway, I'm gonna skip B because that's correct answer. Where A, crushing these particles, what we're gonna see is that the crushing, whenever you say you're gonna crush a solid, that just means that you're increasing surface area. The thing is, increasing surface area, which we mentioned before, what does that do again? What does that do with a solid? If you have greater surface area, I briefly mentioned this thing, so I'm just gonna explain. Increasing surface area will increase the rate of reaction. The thing is, right now we're talking about equilibrium, so not how fast the reaction goes, but what position it is in when it finally reaches its equilibrium state. So crushing the CaOH2, another way you can think about it is that it doesn't change your equilibrium expression, right? I don't see any CaOH2 surface area quantity in this equilibrium expression. So this is not going to be true either. Now, then again, I don't see temperature in this particular quantity. The thing is, temperature is going to be inherent in PV equals nRT for the pressure. You're increasing temperature here, so your pressure increases. There's that effect. Now, it's not a perfect translation, so that's why I brought up the delta H from before. I'm going to clear all this real quick and focus up on that delta H. When you have energy that is significant, like this one, where they purposely pointed out, you can kind of think of it as another compound in your reaction. You can think of it as another factor. So I'm going to go back to that hill comparison. Now you're going to have less energy or less temperature. So we're going to have that. We started out with a flat hill, but now we have less of this. The reaction is going to therefore shift to the left. Therefore, we're going to get more of the CaOH2. This side will decrease in amount. This side will increase in amount. Make sense?
Yeah.
All right. All right. So, Angelina, does it make sense? It's good?
Yeah.
Cool. So that's that for that question. Let me, I'm gonna go back a bit. Let's talk a little bit about rates. So right now we talked a lot about equilibrium. I did mention rates at the beginning, so I want to kind of go back to that. This question is pretty good. Actually, no, that's kind of advanced. Let's see if I can find a simpler one. This one's pretty good. How about this one? Let's start with this one. No, wait, that was the one we just did. No, there we are. All right, so we have this data table where you have following data for A and B, and there's going to be some reaction between A and B, and we're looking for the order of the reaction. So let me define order of the reaction first. Order just means, essentially you can think about it like the rate of a reaction, but it's going to be equal to some constants multiplied by the concentration of your compound to some power. So we have these two reactants in so-and-so reaction. Some amount of AO plus some amount of BO forms products. We don't know how much these are. And what we're going to see is that the rate is going to be equal to, it's going to depend on the concentrations of these, right? We expect that. This is a reaction with these reactants. So of course the reaction rate is going to depend on how much reactants you have, right? But we don't know exactly how it depends. Is it a square relationship? Is it a square root relationship? Maybe it's a cubic relationship or linear. We don't know. And that's something we need to determine either experimentally or with what's called elementary reactions. We're going to go into that a little bit. Here, we're going to look at data. So actual data that you might collect about a reaction. So what can you guys tell me between these two data states? What is significant between these two? Don't be shy. If you have an answer, don't be afraid it's wrong. Just put it out there. Don't talk
They're
about
the
it.
same.
They're the same. Okay. A0 is the same. And what about B0?
It's twice the.
It's twice the amount. Yeah, that's just times 2. All right. And then between these two, what about it?
It's quadruple.
Quadruple. Yes. Times 4. Essentially, we can think about it like we have, this is our initial rate, right? So let's start plugging in some stuff into these equations. That, I'm gonna skip the units. So that's okay. To some power of x, 0.60 to some power of x, 0.40 to some power of y, right? And then we have this one right here, 2800. 0.60 stays the same, x, and then 0.80 y. We can cancel stuff out from this equation, clearly. If we divide the two equations, cancel that out, that's 4. And this cancels out to 2 to the y. Let me move back for a little bit from there. Right, if we have 0.4 to the y, 0.8 to the y, let's first write this out. Basically, I'm taking this equation, dividing it by that equation. All right, does it make sense?
Yep.
Okay. So if I divide them, this side just equals 4 because 28,800 divided by 7,200. We know that's quadruple, so that's 4. The x cancels out. The k cancels out. We're just left with y. So then we have 0.80 y over 0.40 y. If you guys know your exponents, we know that we can do this. And then this cancels out to 2. So 4 equals 2 to the y. What is y?
2.
2. So now we know that the concentration of B is impacting this reaction with a quadratic relationship. So basically, our rate thing right here is going to be 2. I'm going to write that in a different color. We know that's 2. What that means is second order. So the order just really refers to the power. First order just means you have a linear relationship. 0th order means you do not impact the rate, which is possible. And third order means cubic relationship, so on and so forth, so on and so forth. All right, so we know that's second order, so automatically that rules out C and B. So now we have to look at A. So what's the ratio between these two?
Uh, 12.
12
Yep.
times 12. Between these two, that I'll do myself, times 2. But we know that B is impacting by quadratic, right? So that's going to cause an impact of times 4, right? This one we see is times 3. So essentially, A is going to be impacting by times 3. B is impacting by times 2 squared, so times 4. And the ultimate result is times 12. So what is the power that we have on A? How much is A affecting? What would be X in
1.
this case? 1. Yeah. So let's say if this data said times 36, for example, like I'm just putting a hypothetical, then we know this is times 4, then this would have to be times 9, and then we know X is 2. That's if A were quadratic relationship. Here though, A is going to be a linear relationship. So we're going to actually see that this answer is first order for A. First order for A, second order for B. All right, so that's that. Fundamentals of rate. Essentially, you can represent each rate as rate equals some constant times concentration of reactant 1 to some power, reactant 2 to some power, so on and so forth for however many reactants you have. Now, the thing that's different between equilibrium and rate is that how these reactants are related, we don't know. Essentially, this is not X, this is not Y, not like that. Equilibrium, has that relationship where you can look at the coefficient at front and put that. Oops. Shoot. Sorry about that. I think that might be my computer's out of battery. Anyway, let me just quickly finish up what I was gonna say, and then we can talk about it from there because we're almost done now with today anyway. So with equilibrium, you can look at the coefficients and then put those as exponents in your equilibrium expression, right? We saw with the 4NH3, that means that in our equilibrium expression, in the denominator, we're going to have NH3 to the fourth power. With kinetics, with rate laws, we cannot have that relationship. It's more complicated than that. There's other factors going into it, all that stuff. So that's why either you determine it by data or you determine it by elementary rate reactions. That is something that, considering that we only have 10 minutes left and I do not have my computer, it's going to be a little difficult to get through. You guys probably saw the reaction with iodine and all that, where there's like something about slow and fast, reversible, things like that. That's the idea behind elementary rate reactions, which, if you guys are interested, we can go over at the beginning of next time. But anyway, I figured that maybe we could wrap up early for today, but of course I want to first ask any questions at all about what we talked about today, or just in general, any questions they might have for chemistry or biology that you guys want to talk about. I'd be open.
I think I understand the rate thing, but could you go over like the very first stuff about equilibrium again with the coefficients and yeah.
Yeah, for sure. Give me one sec. I'm going to share a whiteboard on this iPad. And I'll write a little bit. Forgive me for turning off my camera. It's just going to be a little easier for me. Anyway, so equilibrium, represented by one constant, KEQ. KEQ is going to be special for every reaction. Each reaction has its own unique KEQ, depending on how the reaction behaves and all that. It's a very molecular thing. And each reaction's KEQ never changes. So even if your conditions change, your KEQ will always remain the same. And that's how you're able to predict how the amounts of your chemicals may change. So let's say I have reactants A and B, that's not equals. I'm going to change it up a bit. I'll say 2A plus 3B goes to C plus 4D. All right, so how would we write this KEQ expression? Well, first of all, it depends on the state of our compound. So I'm just going to put down a few states, kind of randomly. And the KEQ expression for this essentially just means you look at the coefficients of all the non-solid, non-liquid compounds you have. Why is that? That's just how it works because the data tells us that. Solids and liquids are not involved in equilibrium. So for this particular one, we're going to see that's concentration of C over concentration of A. Concentration of, shoot. Give me one sec, my pen's not writing. All the technological faults. Anyway, if that statement were complete, it's a concentration of C over concentration of A squared. So that would be a representation of our equilibrium. So if C were to increase by 4, for example, knowing that KEQ stays the same, how would A change in that kind of case?
Wait, could you repeat? Sorry.
Yeah. Stupid pen. Anyway, if KEQ were to, so KEQ stays the same. If C were to increase in amount by 4 times, how would A change? Oh, hold on.
Increase by 4 times.
Let me write it out real quick. Because it should be working now. Come on. Okay, I'm just gonna write it out
Increase by
again.
8 times, right?
8 times, 4 times. Let's see.
Wait, is there a coefficient in front of the C or no?
The coefficient is 1 in front of the C.
Oh, all right.
All right. So sorry for the bad handwriting. I'm trying to use the finger now. But anyway, C increased by 4 times. So C times 4. That's gonna be times 4 on this side. But then we need essentially to cancel that 4 out with the denominator. So let's say basically we want to just multiply this by 1/4. How would
So
we do
then
that?
A would also would be times 4, right?
But
And
A is squared, right? Keep that in mind. So basically A has a larger impact on any changes. So you can think about it like basically A is going to increase times 2. And that's because
it's the square root of it because I'm assuming you're distributing that 4 times like among the A's. So that would be 2.
you can think about it like that, but you also can think about like if A increases by a factor of 2, that is going to be squared because of its disproportionate impact on the rate, on the equilibrium, sorry. So then you're going to have 2 squared, and that's going to end up being 4. So then you'll have 4 in the numerator, 4 in the denominator, and cancel that. Does that make sense? Because I'm not sure if it explained it well. Is it good? All right.
Yeah.
So that's kind of the essence of rate of I confuse them all the time. Sorry, equilibrium. Don't confuse them like me. When I first learned this, I also confused them, like I am right now in my speech. But they're very separate concepts, and it's gonna be not good when you confuse them because there was a time where I was like, yeah, for equilibrium, you are impacted by surface area of solids and all that. Like, no, you're not. You have to separate those two concepts. And anyway, that's the basis of equilibrium. So with equilibrium, then we can consider different effects that might occur. So for example, if you increase your amount of A, right? And when I say amount, I mean concentration. If you increase the concentration of A, then if we think about that Hill effect, we'll have more C and D. We'll lose a bit of A and B. Now, let's say I increase A, like I mentioned. If I multiply by 2 or something, and then we have this Hill effect. A is going to increase, let's say, by that amount. And therefore, the Hill effect thing occurs. The Hill effect is not the actual name. It's actually called Le Chatelier's principle. French dude who figured it out. But basically, he's just talking about how the equilibrium shifts, as we're describing right now. Anyway, if A increases like that, then we're going to have that shift. So we're going to see increases in our products. We'll see a decrease in our reactants. So A is going to decrease a bit, B is going to decrease a bit. The thing is, overall, A is still going to be increasing, just not by 2 times, less than 2 times, essentially. C and D are both increasing by some amount. B is going to be decreasing by some amount proportional to these amounts, but A is going to still be increasing. Does that make sense?
Yep.
Because A is decreasing, but decreasing from an increased state. So now a little problem for you guys. Let's say A increases by some amount, and that causes C to increase some amount at equilibrium. Let's say it increases X. How much will D increase by equilibrium?
X.
Remember those coefficients, right? If you're forming 1 of C, you're going to be forming 4 of D.
Oh, then 4x, sorry.
4x. All right. Yep. Now, what happens to B in this case?
Well, you're increasing A by X, right?
Yeah. Oh no, we're increasing A by some amount that causes
Oh,
C
that
to increase
causes
by X.
okay.
Because I don't have an equilibrium constant here. I don't have the actual math, so, and it gets really complicated with that. So I'm just saying it increases by some arbitrary amount y, and that causes C to increase by x. From there, though, we should be able to predict all the changes that occur with D, B, and even A.
Shouldn't B increase by the cube root of x?
Ooh, yeah. The powers are not going to be factoring in here. I think this is like, you guys are probably overthinking a tiny bit. This is like stoichiometry, right? So you increase this much. Therefore, first of all, if you increase on this side, you got to decrease on that side, right?
Mm-hmm.
So we're going to see that B decreases in amount. And 2 A's and 3 B's react to form 1 C and 4 D's. So for forming X, let's say if we're forming 1 C, how much B would have been consumed?
3B.
3B, right? Now, let's say you're forming 2C. How much B would be consumed?
6B.
Now, let's say you're forming XC, X amount of C. How much B would be consumed?
3XB.
Yeah, so we're going to see negative 3x over here. Does that make sense? That's just like
Yes.
equilibrium shifts. All right. And then now that I put a value to A, that y, now we can predict the amount of A we're going to have at equilibrium. So A used to be some amount, but now we increased it to y. So first of all, now that you formed X amount of C, how much A are you going to lose from that particular process? Same thing with this.
2XA. Sorry, 2X. Negative 2X.
2x. So what we're going to end up with is y minus 2x for A. And we can write this all within KEQ expressions. If, hold on. I'm going to clear my drawings real quick. The equation was 2A, hold on. Come on. Anyway, 2A plus 3B goes to C plus 4D. 3B goes to C plus 4D. God dang. Finger's much worse. Anyway, so then we can have KEQ represented by C increasing by X. So we'll have whatever C used to be plus X. Then whatever D used to be plus 4X, right? We found these values up to the 4th power. And then B, whatever that amount was, minus whatever 3x, right? That's cubed. And then A increased by y, right? So A plus y, but then we have that minus 2x. Now, I remember I said that D and B were solid, so that's not part of the equation. That's not part of the equation. What we're left with is this thing right here. And that we know will have to be equal to C over A squared, right? Because that's what we had at the beginning with the equilibrium. So that's saying if we started out with A, B, C, D amounts of A, B, C, D, and we change this equilibrium by adding y to A, what goes on? This is exactly what goes on. And then we can solve out for x, so on and so forth. Does it make sense?
Yeah.
Yeah. All right. So I don't think I've done this particular topic full justice. So if you guys want, we can always continue this discussion a little bit into next week's meeting. Up to you guys. We can talk about it when we get there. But that basically wraps us up for today. I'm really sorry about the little tech mishap that happened at the end. It's just like computer being a bull. But anyway, yeah, that wraps us up for today. So thanks for coming, and hopefully I'll see you next week. Bye-bye.
I think you.
Thank you. Have a good day or good night.
You too. Bye-bye.